And actually, Giuseppe Sanfilippo is in Prague, but I think it's Niki Pfeifer who is making the presentation online.
Yes. So, okay. So thank you very much. This is joint work with Giuseppe, and we are going to interpret connexive principles in coherence-based probability logic. Can you see the screen moving? Is it now on the second page?
Oh, yes.
Okay, thank you. So the outline is first some introduction, and then I will present two approaches that we developed in order to model connexive principles. So first, what is connexivity? The basic connexive intuition is that conditionals of the form not A, if not A, then A, so self-contradictory conditionals, that they should not hold. This is intuitively plausible, right? If it's raining, then it's not raining. It sounds very strange. And it also matches the experimental data. So we did some experiments on this. But under the material conditional interpretation of conditionals that is used in logic, however, it holds that these sentences are contingent. So if not A, then A is logically equivalent to A. We aim to cover this basic connexive intuition that these sentences, the self-contradictory sentences, are false by the observation that for any event A, which is not self-contradictory, not a tautology, it is necessarily equal to 0. So 0 is the only coherent value. So this matches the intuition. And now we are going to model these connexive principles. So the motivation is to interpret and check the validity of connexive principles within coherence-based probability logic, and we are going to do that by two approaches. In the first approach, connexive principles are obtained by defaults interpreted by probabilistic constraints on conditional events. That is, basic conditionals are interpreted by probability constraints, and negation of the assessment is considered. And we are going to use the wide scope negation. In the second approach, however, connexive principles are obtained by logical operations on conditional events. So here, basic conditionals are interpreted by conditional events and not as constraints. And here we negate the object, and we use the narrow scope negation. So what are the then connexive principles? Here is a list of connexive principles used in connexive logics. Not all are valid in all the systems, but these are the main principles, and we are going to study these principles. So for example, Aristotle thesis, it is not the case that if not A, then A. Or here, these are iterated ones. If A, then B, then it is not the case that if not A, then B. So the first approach, here we interpret the basic conditional if A then C by a default. So C is a plausible consequence of A, which we interpret by the conditional probability assessment of C given A equals 1. The negated conditional is interpreted correspondingly as a negated default, which we interpret by the wide scope negation. And that is given by just saying that the corresponding conditional probability is not equal to 1. So we interpret the inner negation not A by the overbar, then the conditional is interpreted by the default not C is a plausible consequence of A, and likewise as it is written here. So we first consider non-iterated connexive principles, that is where the key connective is not conditional, and we define it as follows. A non-iterated connexive principle is valid if and only if the probabilistic constraint associated with the connexive principle is satisfied for every coherent assessment on the involved conditional events. So the validity of Aristotle thesis, for example, is given as follows. We interpret Aristotle thesis by the negated default. A is plausible, is not the plausible consequence of not A. That is, the conditional probability of A given not A is not equal to 1. We observe that A given not A equals 0 is the unique precise coherent assessment on A given not A. Then this satisfies the probabilistic constraint associated with our connective principle, and therefore Aristotle's thesis is valid. The validity of AT prime is done in a very similar way. For Abelard's first principle, which is this one, it is not the case that if A then B and if A then not B. This is interpreted by the negation of these two defaults. That is, the conditional probability of B given A equals 1 and the conditional probability of not B given A equals 1. So this assessment is not satisfied. And this principle is valid because coherence requires that these two probabilities need to sum up to 1. So therefore, this is Aristotle's, Belard's first principle is valid. Aristotle's second thesis, which is, it is not the case that if A then B, and if not A then B. So see, this is very similar to this one, but here we negate the consequent and here we negate the antecedent. It is interpreted by the negation of this set of defaults, which is interpreted probabilistically in this way. And we see that this is not satisfied because if you assign B given A equals 1 and B given not A equals 1, which is perfectly coherent, then you have an instance where you see this is not satisfied. So therefore, Aristotle's second thesis is not valid. For checking iterated connexive principles, we need to give another definition, and this is as follows. An iterated connexive principle from where we have some conditional here and some conditional here is valid if and only if the probabilistic constraint of the conclusion is satisfied by every coherent extension from the premise to the conclusion. So this is not p-validity, but this is rather this, again, satisfaction of the constraints. And here, for example, look at Boëthius' thesis, which is this principle here. This is interpreted that if the conditional probability of B given A is 1, then the conditional probability of not B given A must not be 1. And this is valid because not B given A must be 0 when B given A is 1. Therefore, Boëthius' thesis is validated. And also Boëthius' thesis prime is also validated in a similar way. However, reverse Boëthius' thesis and these variations B3 and B4 are not valid. Let's go now to the second approach. Here we, instead of interpreting basic conditionals as defaults in terms of probabilistic constraints, as we have done in approach 1, we now analyze connexive principles as conditional random quantities within the theory of logical operations among conditional events. So this is the second approach. In approach 2, a basic conditional is a conditional event instead of a conditional probabilistic constraint, which is a 3-valued object, so true, false, and void. Logical operations among conditional events yield not conditional events, but conditional random quantities with more than 3 possible values. We will see an example later. And of course, you must not nest conditional probabilities, but you can do that with these conditional, with these logical operations among conditional events. So the definition of the second approach of the validity of the connexive principle is very elegant compared to the first one, because this is one definition which suits all the connexive principles we consider. A connexive principle is valid if and only if the associated conditional random quantity is constant and equal to 1. So this is the important definition. So now let's have a look at how to interpret the conditional event as a conditional random quantity. Given an event A, we denote by the same symbol in its indicator, which is equal to 1 or 0, according to whether A is true or false. Let P be the assessment on the conditional probability A given H, be a conditional probability assessment on this conditional event. The indicator of A given H, which is denoted by the same symbol, is defined as the following random quantity. So A given H is defined in this way, and it is 1 if A and H is true, it is 0 if not A and H is true, and in some sense you get your money back if the conditioning event is false. So these are the usual conditions. Of course, the third value of the random quantity depends on the assessed probability of the conditional probability. Now, a conditional is interpreted as a conditional event where, or we have this equation here. We interpret, it is not the case that if A then B by this formula here, the negation of the conditional event is defined simply by the 1 complement. And now we can prove the validity of Aristotle's thesis. We interpret Aristotle's thesis, this is this formula, by this object here. And then as this one holds in general, we obtain that Aristotle's thesis is constant and equal to 1 and therefore validated. In a similar way, we also validate Aristotle's thesis prime. For Abelard's thesis, we interpret Abelard's thesis, this is this one, with this object here. And this is a conditional event because we condition always on A. So in this case, it is in some sense a bit simpler. Of course, we assume that the conditioning event is not the contradiction here. We observed that this formula here, this conditional event here, reduces simply to the empty set given A, which is of course 0, and then the negation of this becomes 1, and therefore Abelard's thesis is validated. For studying Aristotle's second thesis, where the conditioning events differ, we need to have a definition of conjoined conditionals as conditional random quantities, which I present very quickly here, and more. You will learn more about this by Giuseppe's talk at the end of the week. So given any pair of two conditional events, A given H and B given K, with the corresponding assessments X and Y, the conjunction is defined in the following way. We have these 5 conditions here. So in the betting framework, you agree to pay the value set for the provision in this object, with the proviso that you will receive 1 if both conjuncts are true, if both conditional events constituting the conjunct are true. You get 0 if at least one of the conditional events is false. You get the probability of that conditional event which is void if one conditional event is void and the other one is true. These are these 2 conditions here. And you get the quantity, you get your money back if both conditional events are void. So this is the definition of the conjunction of 2 conditional events. And this allows us to interpret this object here. This is Aristotle's second thesis, because this is the conditional random quantity B given. It is not the case that B given A and B given not A. And here we get these semantics here, which is not constant and can therefore not be necessarily equal to 1. And in particular, for example, if you choose that X and Y is 1, which is coherent, you get this one reduces just to not B, which is not necessarily equal to 1, as it could be either 1 or 0, depending on whether B is not B is true or false. And in a similar way, we can go through these connexive principles. Therefore, Aristotle's second thesis is not valid. For the iterated conditioning, we also need a definition of iterated conditionals. And recall the definition of the conditional event, which is given here. So true, false, and void, if you like. And the structure of the definition of the iterated conditional is in a very similar way. So instead of having here A and H, we have here conditionals, box and circle. And then we see the definition is the same, obtains the same structure as the definition of the iterated conditional obtains the same structure as the definition of the conditional event up here. Sorry, where is it? Here. So this is the same structure as what we have here, with the difference that here we have conditional events and here we have atomic conditionals. Atomic events. So in explicit terms, we obtain the definition of the iterated conditional here, B given K, the whole thing given A given H, and we have these 7 conditions here. And these 7 conditions are, of course, much more complicated compared to the 3 conditions that we have for the conditional event. But this is necessary in order to avoid Lewis's triviality results. So with this semantics, we can validate Boëthius' thesis, where Boëthius' thesis, this is this one, if A then B, then it is not the case that if A then not B, is interpreted by the iterated conditional, the negated conditional not B given A, this one is negated, given B given A. And going through all these details, we obtain that by coherence, it must be that the value assessed here is 1, and therefore, this object is constant and equal to 1, which validates Boëthius' thesis. Here is an overview of all the connexive principles we considered in the second approach. Here you see whether they are valid or not. You can see all of them are valid except for Aristotle's second thesis, and also the Boëthius variation number 3 and 4, they are also not valid. And here you see the interpretation in terms of conditional random quantities. Here you see the connexive principles. And with the contrasting this with the first approach, we note that RBT and RBT prime are not valid in approach 1, whereas here they are valid. So this brings us to the concluding remarks. Connexivity, this idea that self-contradictory conditionals should be false, is not only psychologically plausible, but also emerges naturally under probabilistic interpretations. Specifically, we recovered various connexive principles via two approaches. Approach one interprets connexive principles by defaults, which are interpreted by probabilistic constraints and conditional events. That is, basic conditionals are interpreted by probability constraints, and negations, that the assessment is negated, and we use the wide scope negation. In the second approach, connexive principles are obtained by logical operations on conditional events. The basic conditionals are interpreted by conditional events. The negation of the object is negated, and by the narrow scope negation. We showed that Aristotle's second thesis, basis variations 3 and 4, are not valid in both approaches. And we also aim to show that, let me also mention that coherence-based probability logic allows for bridging qualitative and quantitative principles, and applications include, for example, we've developed some semantics for Aristotelian syllogisms, for the squares and hexagons of oppositions in terms of probability and defaults. There is a lot of work on non-monotonic reasoning, like on system P, or on weak transitivity and other rules. And we also obtained some results concerning aversion for the towards the deduction theorem, using this idea of logical operations on conditional events. On the paradoxes of the material conditions, they are blocked by the semantics. And there are many experiments in the psychology of reasoning, and so on. So future work concerning this is also to analyze other connexive principles, and we are happy and interested if you have any suggestions to generalize what we do. Thank you very much for your attention.